Shota, are you recording? No. Okay, great. Sean, please.
Thanks, Shi, and thanks to the organizers for putting together this nice conference. And it's certainly nice to be at a conference without jet lag, and it's good. So I changed my title a little bit from what I think the organizers might have wanted, but it will mostly be what the organizers wanted. However, I know that some people in the audience have heard a version of this talk somewhat recently, so I added a few. That's why I changed the title and added a few little things. So I'm going to be talking about work in collaboration with my student, Xixia Han, and with the postdoc at Stanford, Yorit. I'm going to talk about two papers, and but I should really stress that Xixia is responsible for about 90% of what I'm going to say. All right, so now I think I don't need too much motivation in this talk, maybe in this context, but perhaps given that there have been a lot of talks on C=1 and so on, I just want to stress that I really think that understanding multi-matrix quantum mechanics is essential, and assuming humanity doesn't go off the cliff at some point in the next few years, if we eventually make it to the theory, really understanding where space-time comes from, I don't know at what point, but I think at some point we're going to really have to understand multi-matrix quantum mechanics. And so I think we need to do what we can in that direction. At some point or other, we're not going to be able to avoid solving this problem. Okay.
So quantum mechanics is enough, but just not a single matrix. Just to clarify.
Let me include quantum field theory. Let me think of quantum mechanics as the simplest case of quantum field theory. But quantum mechanical system with matrix degrees of freedom where there is more than one matrix and they don't commute. That's what I mean.
Okay, thank you.
And related, so I think my suspicion is that, so if you have one matrix, you can diagonalize it. I should say that non-singlet sectors of single matrices are more similar to multi-matrices. Right? But if you can just diagonalize the matrix and just think about the eigenvalues, well, those are particles. We understand a lot about particles, and it's probably not enough for black holes or sub-ADS or substring scale locality. And I suspect that we will need to grapple with the intrinsically matrix wave function. Okay, I mean, we know how to write down wave functions for particles. Okay, that's just normal quantum mechanics. But it's less obvious what a matrix wave function should look like. And one reason for thinking this is that the throats in ADS-CFT, where we understand emergent geometry, I mean, you really have to put the brains on top of each other. A bunch of brains very well separated, that's not an emergent space, it's just a bunch of separated brains, okay? And so this holographic limit, I think, is fundamentally different from the Coulomb branch, which are these very separated eigenvalues. And so a fantasy that one might have is that, at some point, someone will write down something analogous to a Laughlin wave function for matrix quantum mechanics, which would be a toy wave function that shows how matrices have to be entangled for emergent locality and emergent space-time. In the same way, the Laughlin wave function, I mean, it's not even, I think I'm trying to redirect attention towards the wave function from, it doesn't matter if it solves a Hamiltonian or not, okay? What is the entanglement structure that matrices need to have so that the emergent, so has some emergent locality, okay? But we're not going to get there today.
Sean, can I ask, when you say this Laughlin wave function for matrices, do you have in mind what is this wave function a function of?
Well, that's a good question. I mean, it could be traces of matrices is one way to write it, or it could be a function of the components of the matrix with some gauge constraints. Indeed, so it's not even obvious to me what the most transparent way of writing these wave functions is going to be. I mean, right? So the obvious variables are traces of strings of matrices, or in some kind of more gauge fixed version of life. I don't know. Is that what you meant?
Yes, because if you just write all components of the matrix, there will be way too many degrees of freedom to keep track of. It's hard to imagine how one can characterize such a wave function in a useful way in the general, which is quantum mechanics.
Well, I mean, there are a lot of electrons in a quantum Hall droplet. I mean, I think I don't think it's impossible that we might understand what the essential structure is, but it's just offend. So I think that the objective is to understand quantum aspects. Okay, we do understand some things about matrix quantum mechanics from non-zero temperature quantum Monte Carlo, classical Monte Carlo simulations, and actually things match, and that's very nice. But I think I'd really like to try to grapple with the quantum zero temperature aspects, and I'm going to say by any means necessary, right? So I'm not going to have any principles about, let's say, not using numerics or stuff like this. Okay. And I'm going to outline two approaches that we've taken recently. One is a variational wave function, and second, I'm going to talk about bootstrapping. So the focus of this talk will be the bootstrapping approach, which I think is what the organizers wanted. But I just want to briefly mention the other approach too. And so, you know, variational wave functions are a bit in this Laughlin spirit, right? They're just going to make up a wave function. And actually, these are a bit complementary. We're going to see that one thing that variational wave function gives you is a rigorous upper bound on the energy. And these bootstrap approaches are going to give you rigorous lower bounds on the energy. Okay, so possibly combining the two is useful. And so variational wave functions have an intrinsic problem that you don't know how good it is. Okay, but one thing it does give you is an upper bound on the energy. Okay, so let me just quickly talk about this variational wave function. Now, the problem is, so, you know, for example, one instance of useful variational wave functions are matrix product states and tensor networks and so on. But there you know what you're doing. You know that locality is crucial, and what a tensor network is designed to do is a variational wave function that is built to exploit simplifications due to locality. In the case of matrix quantum mechanics, we don't know what the simplification is in terms of the matrix degrees of freedom. And so therefore, and that's what we like, that would be the output. We'd like to understand if there's a simplification. And so we'd like it as unbiased approach as possible. And that's sort of what these neural networks are. So neural networks are ways of approximating nonlinear functions of big variables that seem to be quite robust, meaning they can find structures that might not be obvious a priori. And so the direct inspiration here is there have been recent successes using neural networks in the context of spin systems, which is also a many-body system, right? So matrix quantum mechanics is a many-body problem, right? It's not a conventional one, there's no locality, but you can think of it as a many-body problem. Very good. So motivated by that, we tried this. And so the main point of the next 10 minutes is I just want to demystify this if it needs demystifying for anybody. Okay, it's very simple. Okay, so all the neural network is a variational wave function. Okay, so there's going to be, so it's a function, okay, that depends on a bunch of parameters. You feed it some coordinates and it spits out a value, okay, which is the value of the wave function as a function of the coordinates. So the xi would be the entries of the matrix, for example, and the a, b, c, d are the parameters that parameterize the wave function. Then as with any variational wave function, what you do is you try to minimize the energy. You minimize the energy in the space of these parameters. Okay, and that's easy to do numerically using gradient descent. Okay, so this is called self-learning or something, I forget the word. Right, so this is not like there's some data set that you're trying to learn from. Okay, it teaches itself by trying to minimize the energy. Right, so it's just a variational wave function. Okay, so let me just tell you how you build this thing. And so it's also in principle not complicated. Right, and so. Right. So what do you want? What's a wave function supposed to give you? So a wave function is a probability distribution of x squared. That gives you some probability, and with that you can calculate energies and so on. So what you have to be able to do with a wave function is to be able to sample from it. Right. So if you can sample from some probability distribution, then you can calculate stuff using Monte Carlo. Right. So x tilde p means sampling x from p. Right. Now, so one way to do it, so you want to build a complicated distribution that you can nonetheless sample from relatively efficiently. And so the way you do this is the following. You start with a simple distribution. So for example, y1 to ym, for example, they could just be the entries of all the matrices. Okay, and you say, let's say these are all, they have independent Gaussian distributions. The point about that is that, you know, it's easy to sample. People have already worked out how to sample from Gaussian distributions. Okay, there exist pre-written algorithms to say, give me a sample from a Gaussian distribution. Okay, so you start with a variable y, that a vector has multiple components that has a simple distribution. Then you take this and you feed it through a function through the neural network. So if I have some function f of y, like for every y I get an x. So I do the following: if I sample y from some distribution q, and then I calculate x, this x will have been sampled from some other distribution px. Okay, and it's just from some chain rule is given by that. Okay, but the thing is, if I have a way of sampling from Gaussian distribution, I have a complicated function, I can generate a way of sampling from a complicated distribution. Right? And this f is going to be the neural network. So let me quickly explain how that goes. It's also, so my point is this is not complicated, right? You just take n squared, whatever, 3, 11, 9 n squared, whatever you want, and you take that many Gaussians, you feed it through some function, and that gives you, and you think of that as sampling from your wave function.
Sean, can I ask a question?
So, yes.
Do you know a priori that the wave function is positive, that there's no sign problem?
No sign problem. Yes, I think, yes, you do. Very good. That's a good point. Yes, I think you do, because you look at this function. So P here is manifestly positive.
No, but certainly there are some interesting wave functions where, you know, where
no, but we're getting, these are the probabilities. These are the probabilities. So, and if you have several components, like if there's a phase, right, good, very good. So you have a different network for the absolute value and for the phase. So each function is gonna be calculating a real number, and you want to split off the phase. But this can definitely deal with phases if that's what you're asking.
Okay, I see.
And so maybe you guys have seen this. So this is a simple. So what? And the function is the following thing: you take your initial quantity, just like all the entries of the matrix. You do I guess an affine map to it, right? So you multiply it by a matrix A and you shift it by B, and that gives you a new thing Z. And then you take your Z, that's a linear step, right? So you're trying to build a function and it's a sequence of linear and nonlinear steps. So first you have this step, and then to each element of what you've got, you apply tang to it, okay? And that's your nonlinear function that you apply element-wise. Because this thing is totally breaking any symmetries that you had. Right, and then you do this over and over again, and if you do it 5 times, it's called deep learning. Okay, so you do it some small number of times, and that's called deep. So this is just a function, and it's parameterized by a bunch of matrices that are called the weights, and a bunch of vectors that are called the biases. All right, and this structure, just to use a popular phrase, it is what it is, and it seems to have worked for in many circumstances. All right, so we're just using it to see what happens. So, sorry, any more? Okay, so now I'm going to quickly outline some results, but I'm happy to take more questions.
So what's the rationale behind the choice of the tanh?
Yeah, it doesn't matter too much. And actually nowadays there's this ReLU, which is something like that. There are different, I don't think it doesn't depend very strongly on the activation function. I mean, the original motivation was it was supposed to be like neurons firing, I think. But I think the main thing is that there's a nonlinearity in there.
Okay. So is it important that it saturates at large Z?
I'm not sure, but I suspect so.
Okay.
So are you saying that the wave function is actually Gaussian and some crazy variables?
No, no, because this is, no, that's right. It's not, no, that's right. It's not that the, no, it's not that the wave function, right? If there's this determinant factor and sorry, this is the measure. And no, sorry. So let me, I don't think so, because this is it's the probability distribution. But let me think again. I don't think so. But let me keep that in mind.
And
did you say that you're gonna make a similar treatment with the phase as well, or?
Yes, well, in fact, they're going to be fermions, and so what it's going to be, there's going to be a whole bunch of components of like each different fermion occupation number will have its own number in front. Yeah. Yes. So yes, the phase. Yes, that's right. But in particular, that would include the phase. Yeah. Yeah, that's right. So let me show you the kind of things you can get out. So as an example, we used, I think, following a name that Tarek introduced. There's this mini BMN, and so that's a supersymmetric quantum mechanics with 3 bosonic matrices. Okay, so there are 3 of these X's, and the mini BMN is because it has this sort of mass deformation type term. All right. Okay, and so there's some fermions and some bosons and so on. So a nice thing about this model is that at large nu, and this is the BMN bit, it has a fuzzy sphere classical solution. So this classical potential is just minimized on a fuzzy sphere, okay, whose radius becomes large at large nu. And so there's a regime where you have a hand where you know what the answer is, which is certainly a good thing for these models. So I'm mainly just trying to whet your appetite, I guess. So here, this is the expectation value of the radius, which is defined like this: the sum of the traces of the xi squared. This is as a function of nu, because it is one dimensionless parameter in this model. And these are right. So the bootstrap stuff I'm going to tell you about is good for n equals infinity. Here one is, the bigger n is, the harder the numerics are. And it's particularly hard because there are these fermions that you need to deal with as well. So this is n equals 2, 3, 4, and 6. And this is the radius as a function of nu. And so these dashed lines are the exact semi-classical answer, okay, the exact classical answer. So it finds that the network can find this fuzzy sphere, okay. And now the interesting regime is the quantum regime at small nu. And there's some kind of stabilization going on there. So this is the more interesting regime. So we can zoom in on that a little bit. I should say that for n equals 2, this model was solved numerically, just by solving traditionally by just solving the Schrodinger equation with a bunch of variables by Tarek. And we can, for n equals 2, we can get his results pretty much on the nose. And so one thing that a qualitative feature that you can see at small nu is that the radius starts getting bigger again, right? So there's a collapse of the fuzzy sphere. That makes sense, right? It's just tracking the nu. But as nu goes to 0, if there is a stabilization, it has to be quantum mechanical, and that's going up. I should say that there's probably, you might expect it to diverge as nu goes to 0, and that's yeah, actually that was already a confusion in Tarek's paper, actually, whether they're normalizable wave functions in the master's case in this model, which they probably shouldn't. Yeah.
Sorry, can you be more explicit about the treatment here? So with the fermions, do you just look at a wave function of many components and treat one?
Yeah, I didn't want to go into it. Yeah, but so in practice, there's a truncation. So we consider not all possible fermion occupation numbers, but a handful, and that's a number you can play with, and you right at some point that's right. Yes. So there are some simplifications that definitely go into this. Yeah. And the whole point, right, is not, yes, right. Yeah. It's not the most general wave function. So mainly, yeah.
Sorry, in this model, there is only one adjoint fermion?
Yeah, I think that's correct. Sorry. It has a bunch of, it's complex, right? I think. Yeah.
Yeah, one complex adjoint.
Yes, I think that's correct. Yes. Right. So yeah, and so there we go. So mainly, I just wanted to show you that you can. I think it's not crazy. You can recover known results, including the semi-classical limit and the quantum n equals 2 case. And I would like to, I think it should be pushed. You need more computing power, get to bigger n, get maybe deeper into the quantum regime. But in principle, I think this is not a crazy approach. Okay.
Sorry, in your plot, this the color band that represents the error bar.
Oh, no, it doesn't. Sorry, thank you. I'm sorry. No, actually it doesn't. Yeah, it's not the error bars. It's the variance of the radius of this variable. So this is a bit. It's how quantum. It's yeah. Thank you. Yeah, that's good. So something useful about getting your hands on real wave functions. So this is actually a wave function. You can start thinking about it. And so I want to mention two non-numerical things that are in this paper that I learned that I thought were interesting. One was well known, but not to me. But I think it's pretty cool. Or maybe this is very well known. Someone can tell me this is very well known. But so at large nu, there's this classical fuzzy sphere solution. And you can look at fluctuations about the classical solution, which people did actually, and you get some modes. But there's an emergent U1 gauge field on, it's a D-brane, right? It's basically a single D-brane, this blown up sphere. And so you get an emergent U1 symmetry on a sphere, okay, a local gauge symmetry. And actually it turns out that gauge symmetry is exactly the SUN gauge symmetry of the matrices that you started with. So if you take the fuzzy sphere background plus a delta X, you act with an SUN transformation on that. In terms of the collective variables, it precisely generates a U1, local U1, actually. I mean, you have to do this map in non-commutative geometry. There's a map between matrices and functions. You apply this function, and so here's a case where the SUN becomes a gauge, by which I mean local symmetry. And actually, there's also some area-preserving diffeo involved in that as well. And I think this was one of the reasons that people were interested in non-commutative geometry. Actually, that you can get emergent local symmetries. Okay, so I just wanted to tell you that.
Why is it just a U1?
It's a local U1.
But
so in fact, it's a non-commutative local U1. Is what if you take nu strictly to infinity. So it's a U1. Okay, I'm sorry, I lied a little bit. It's a U1 plus area-preserving diffeo.
So I mean, naively from the D-brane point of view that you were just describing, shouldn't there be like n D-branes wrapping that fuzzy sphere?
No, because there's n that puffed up. So the n D0s, if you like, have formed one D2. That's right. It's like
okay. The D0 number is the flux. Yes. Thanks.
Oh, very interesting question. There should be, in fact, other configurations where you can get non-abelian, brains and stuff.
Well, there are other configurations that's well known, right? You can definitely get an non-abelian enhancement that's all well established.
Yes, I agree. It's yeah. Let me. Yes, I agree. So anyway, yes. Okay, good. Because this possibly is relevant for these questions of entanglement and. Ryutakyanagi is supposed to be some entanglement contribution from diffeos, and if it could be directly related to an SUN, that would be interesting. All right. And secondly, the other thing that we did, which was easy to think about with the actual wave function, is that we defined, I mean, only semi-classically, so it's not extremely impressive, but about the fuzzy sphere solution, we defined a factorization of the matrix quantum mechanic Hilbert space about the fuzzy sphere, which in the large nu limit corresponds to a geometrical locality, factorization of locality, right? Because there should be an emergent area law in the entanglement, okay? And you could ask, how do you see that in matrix quantum mechanics? Because you don't have an area, the matrices don't come with the notion of area, right? And however, close to the fuzzy sphere, there's a non-commutative geometry, and so you can sort of define a non-commutative area, and we could get an entanglement like that. Very good. Okay, so I want to move on and mainly focus on the next bit, but let's see. Are there any more questions about that?
Yeah. So in the cases like the fuzzy sphere, the system has you have this large parameter nu, which is driving a sort of a steep potential well that the matrices want to find. So have you explored how good this strategy is at finding ground states or low energy states of things with complicated potentials? I mean, I have in mind, you know, things. Well, so like this matrix quantum. I guess if you low nu, yeah, you have this commutator squared, and classically that has some kind of chaotic behavior.
That's right. So the current. So I would say that so a low nu with n equals 2. I mean, again, which you can solve by normal methods. I think n equals 3 or 4. You might have difficulty solving just the normal methods. So we can reproduce n equals 2 for all nu, right? And so that including small nu. And I would say that at these higher ends, there's a qualitative feature which is this upturn of the radius, and that's due to, I think I would say, a quantum mechanical stabilization of the radius as opposed to a classical one. But I definitely agree with the spirit of the question, and I would, yeah, one should look more at small nu.
You have any sense of how large an n you could get to with current, you know, computational power?
You know, no. I mean, I think it depends on a lot of things, like how simple, you know, and there's not a unique way of doing this. I think n equals 100, definitely, probably not, right? 10, probably. Yeah.
Okay.
Okay, so on a different well, actually, sorry, let me see what would be, so what you can definitely get like this are upper bounds on the energy, okay, because that is just a rigorous thing. And if there are other problems, I know there may be different kinds of questions and different kinds of models that might be interesting to think about. I'm trying to say a good strategy might be defined by.
I was just wondering, I mean, the strategy is some kind of gradient descent. And so if the potential landscape is sufficiently complicated, there might be some sort of, you know, glassy frustration that keeps you from finding things.
That's correct. That's correct. Okay, so on a different note, so now I want to talk about bootstrapping. I think maybe this might appeal more to the audience, but let's see. So this was directly inspired by a very nice paper by Henry Lim from a few months ago, and it's the first time in a long time that I just saw a paper and like, okay, you know, we can that's something we can work with, and we straight away tried to generalize it to the quantum case. So Henry's paper was on large n matrix integrals. And the basic idea is to use positivity constraints to bound the solutions of these models. I should say there is some history of doing this, both classically and quantum. And so the possible importance of positivity was mentioned a long time ago by these authors. And actually more recently, this paper by Anderson and Puchensky on lattice gauge theory at finite temperatures has a morally rather similar approach. And actually, even in the quantum case, there's actually a long history of using positivity constraints in quantum chemistry. So let's say you want to understand the wave function of a medium-sized molecule. There, for example, you can find papers by Mazziotti that basically use positivity constraints. In his case, on reduced density matrices to try to understand the problem. Okay, so I'm not making up the method, but we're going to apply it to matrix quantum mechanics. And so the idea is that we're going to relate the expectation values of simple operators to expectation values of slightly more complicated operators. We're then going to impose some positivity constraints on these more complicated operators, and that'll be seen to strongly constrain the simple operators. And so by positivity constraint, I just mean, you know, expectation value of x squared is positive, right? That kind of thing. So let's do this in 3 steps. So as a warm-up, let's do the anharmonic oscillator. Then I'll do 1 matrix quantum mechanics, and then I'll do 2 matrix quantum mechanics. So this is of course the anharmonic oscillator, and so we're going to bootstrap the anharmonic oscillator in 2 steps. So the first thing is going to be to get a recurrence relation between expectation values in an eigenstate, and then secondly, we'll constrain those expectation values. And so the way to get a recurrence relation is to use symmetries. In this case, time translation invariance, which gives you that symmetry, right? The commutator in an eigenstate, right? Maybe I don't need to spell it out, but just in case. It's HL minus OH. And so if that's on some eigenstate, then you can act to the left, you act to the right, and you get 0, right? Energy minus energy. So is that clear? So maybe I can EIO minus EIO, which is 0. Okay. So now for this anharmonic oscillator, we can really do it very explicitly. So let's take O to be x to the s, and also to be x to the t times p. You plug these those two quantities into that equation. You do some very elementary commutation relations, and whenever you get p squared, you eliminate it using the Hamiltonian, right? So for an e, right? So p squared plus x squared plus gx to the 4th, acting on psi is e psi, right? So we can eliminate p in terms of e and x's. So if you do that, you get this relationship, which is a recurrence relationship between expectation values, right? So this is x to the t minus 1, t minus 3, t plus 1, t plus 3. And so what that shows you, and in fact, if you stare at this for a second, you can see that all expectation values x to the 2t are determined by the energy and by the lowest one, which is x squared. Okay, it doesn't look like it because there are multiple terms, but many of them are 0 at low t. Okay, so then we're ready to apply the bootstrap philosophy, right? We're going to scan over e and x squared, calculate a whole bunch of higher expectation values, and impose some constraints on them. So this constraint in this case is extremely similar to what Henry talked about. And so you can do the following. You can take any linear combination of powers of x, right? So these c's could be negative, right? So for example, this is O could be c1 plus c2 times x, for example, okay? Then O dagger O had better be positive, all right? And so that becomes something like a matrix like this, c1, c2, 1 x, x, x squared, c1, c2 should be positive, right? And so this is much more powerful than just squaring individual, x squared, right? That's sort of that's boring. But by allowing these c's to become negative, you get a much stronger set of constraints, right? So this whole matrix has to be positive, right? So in general, that's this matrix, right? So there's if I truncate at k, right? So I consider a sum of these operators up to k. I get a k plus 1 times k plus 1 matrix, and that must be positive semi-definite, okay? So now it's pretty easy. You fix k, you scan over e and x squared, you calculate the lowest eigenvalue of this matrix, and you require that it's positive and non-negative. Yeah? And so if you do that, this is what you get. So in fact, to give you a bigger picture, so there's going to be an energy x squared plane, right? It's like a bootstrap thing, and there are going to be a bunch of little islands looking like this, okay? And so now if I zoom in on this lowest island, it's like this. So look, these are, it's not a big range, okay? And then here we're increasing k, and this is, of course, we know the answer, and so you're converging on that red dot. So this is the ground state, and this is the first excited state. And of course, you have to go to sort of larger k to get more information. All right? So this is a rather efficient numerical way, should you ever want to find the spectrum of an harmonic oscillator.
Can I ask a question? Sorry, can I ask a question? So this is the result for like a positive x squared, right? The potential. Is there any like a difficulty associated with the double well potential?
Yeah, thank you. Yes. I don't know actually. So I should since you wrote this paper, all the authors got distracted, and there are many natural questions that are not going to be that. Yes, indeed. So yes, I don't know. I don't know. It's the bottom answer, and it would not take much time to answer that question. I mean, you could easily set it up, but I don't know the answer.
Sorry, why would there be any qualitative difference for double well potential?
Well, from this point of view, like I don't see any difference, but like from other approaches, like there are the structure is more complicated, I think.
Yeah, and this, yeah, I agree with that. And I don't know, but somebody, it's definitely answerable, and then yeah, someone should answer it.
I have another question. If I want to compute correlation function at different times, is that straightforward? Or I mean, of course, it turns out
so
expand out the propagator, but I mean.
No, you can definitely, and maybe Henry might want to talk about that later. I'm not sure. You can definitely set that up. And I think now, if the system is chaotic, the operators are going to grow, and you know, so this, like the K that you can get, this is going to be, you know, here you might be able to do something, but you're going to need to have very large K probably to be able to access the operator that you want, because it'll grow, right? So long in this approach, right, is to start with simple operators related to complex operators. But if the operator that you care about, if x of t, right, under Heisenberg evolution, grows long, that intuitively seems like it might make it difficult. But I'm not sure. So that makes sense.
So in this approach, so you will literally just expand this out in powers of t and do the same thing, or is that what you do?
No, I mean, you could, well, maybe ask this question later for the matrix quantum mechanics, because so here, you know, it's a bit misleading because there's this nice closed form relation, this closed form recursion relation and everything, which there's not going to be later. So what's going to happen later is it's just you're going to take a set of operators and bootstrap on it, okay? And if you want to follow the time evolution, that x of t would have to be, yeah, maybe can I come back to this later? I think it'll make more sense in that context. The short answer is, I think that if the operator grows along in a, you know, irreducible way, meaning not that just you chose the wrong basis or something, that it will be difficult to get to times when the operator is long. That's my intuition.
In principle, we could use the Schwinger-Dyson equations, but I don't think that's been attempted yet.
Right. So from an operatorial point of view, it looks difficult, and that difficulties may or may not be, you know, independent of the approach. But intuitively, late time evolution, chaotic system is difficult, right? Yeah. Good.
Another question. Sorry. So in this approach, it seems to be quite essential that say the potential is the polynomial form. Is that true?
Yeah. Well, let's see. In the sense, well, certainly that's right. So what you're going to see later is we're going to have a set of operators O, and you do want H of O to keep you within that set of operators, right? So the simplest case of that is that the operator is a polynomial and the potential is also polynomial, and that there might be other cases.
You might be able to try non-polynomial potentials if you impose positivity amongst non-polynomial operators.
That's what I just said, right? So yeah, if you want, right? So if there needs to be some closure, but which polynomial is the easiest case?
Sorry, how do you, Sean? Maybe I didn't understand. How do you make the islands shrink?
Say again.
How do you make the islands in your next plot shrink? Or you can never make.
I'm increasing so this K here.
Yeah, but does it make them shrink, or it gets stuck?
It's shrinking, right? This is blue, red, green.
Yeah, but the question is, does it shrink to 0 eventually, or it just gets stuck?
Yes. No. So that's right. So I think it's a theorem that when K goes infinity, you have the spectrum.
Oh, okay. Thank you.
Basically, because if you think of it as a density matrix, and let's see how that goes. Okay, it's in a footnote in our paper. Let me just leave it at that. But I think it has to converge at infinite K. All right, so let's see. So let me say something about one matrix, right? So again, the point here was to take baby steps towards the case we want. So we're going to take this model, this x to the fourth. And okay, so the strategy is similar. So time translation invariance gives you this relationship between operators. So for example, if O is trace of xp, and you compute the Hamiltonian, you get this relationship. This is basically the virial theorem, okay, in essence, right? Because so that's one relationship, and then we're gonna be interested in gauged matrix quantum mechanics, and so there's going to be a generator of gauge symmetries, SUN. This is just this Ni is to enforce that the trace is zero, right? So X, there's some operator ordering here, and so right. So actually, we don't even need this trace, okay? But it turns out that it's okay to have it. So I take any operator I want, and I take this generator, and trace of that should be zero because G annihilates physical states. Okay. And so an example of that, so from the fact that trace of G is zero, and using this relationship for x squared, you get the trace xp is minus trace px is n squared. So these are just very simple examples of the kind of relationships you can get between operators. Okay, so however, what we're not gonna, last time for the anharmonic oscillator, we had this closed form recursion relation, and that was basically because we could eliminate p squared. However, it doesn't work so well with matrices, but there's also matrix multiplication, and you can get some, trace xp, or something like that. Okay, and it's not obvious how you're going to turn that into a p squared. Okay, so we have to keep the p's. And there's not going to be a closed form recursion relation. So what we do is take a selection of operators and then put those write down this operator, O is the sum of Ci, Oi. These are the coefficients, and these are some operators that you choose, including x's and p's now. And then from there, you write O dagger O should be positive, okay? And that gives a bunch of constraints on the expectation values of Oi. So for example, if I take the identity x squared, x, and p, right, and I write down a general operator that's a linear superposition of them, and I require that O dagger O be positive, I get this matrix, and so this matrix of expectation values, and that has to be positive. Okay, so I've got a constraint on a positivity constraint on the expectation values. Yeah, so this matrix is analogous to this xi plus xj that we had before, and now it has x's and p's in it. Yeah.
Did you just use large N?
No, not yet. No, there's no large N.
What? Oh.
So
why
I just
multiple traces?
No. So it's not these things. There's no trace here or here. So I take these operators. Sorry. Thank you. Excuse the soundtrack. Okay, so the constraint is the trace O dagger O is possible. Right. So the O's I'm not putting the trace on. I square them and then I put the trace on. Yeah, thanks. So this thing certainly has to be the expectation value of this matrix has to be positive. But then in the previous page, I showed you some relationships between these operators, right? So we know trace px and trace xp. We know. And trace p squared we know in terms of x squared and x to the fourth. So I also know that guy. And so the positivity of this implies a bunch of conditions, including, for example, this one. Right. So the strategy is going to be you take some set of operators, write down a constraint on their expectation values, use all possible relationships that you have between these operators. Right, then what happens? Very good. So we're going to take all strings of x's and p's that have length less than some L. They're of order 2 to the L, such strings, right? Because you have the x and the p at each entry. That gives you a matrix of order 2 to the 2L entries. Okay, now then, so that's some huge matrix. Now you write down all relationships of the type we just discussed between. Right? All the entries in the matrix are expectation values, right? So we relate as many of them as we can. It's basically you take all the operators, you calculate this, right, and use it, and also this. And then you also have another constraint, and this is the first place the large n comes in. We're going to impose large n cyclicity, right? So if these things were not operators, if these were numbers, then of course trace xp cubed would be equal to that. But they're operators, right? So as you cycle, you have to commute them through, right? And when you do that, you do generate multi-trace operators, but at large n, we factorize this, okay? And so this is now everything else was linear, but this is now a quadratic relationship between expectation values that holds at infinite n, okay? Now that's the only place where infinite n is going to be used. So at infinite n, you expect there's going to be a continuum of energies that's allowed by these positivity constraints, right? So that there's in some space of expectation values, you should think that there's let's say this is some expectation value, maybe trace x squared. This is some energy, and there's sort of some cone that's going to be allowed. Actually, it's not a cone because it's not linear. And so what you do is you have all these variables. What we then do, using gradient descent again, is but we're in better shape now because there's some. It's a nicer problem. You minimize the energy of all the subject to all these constraints. Right, exactly, right? So you have a bunch of expectation values, they obey equalities, and they obey inequalities. And on this set, there's well-developed algorithms that to do gradient descent in such a space. And so you try to minimize the energy, right? And so the lowest allowed energy will approximate the ground state. And in fact, it's going to be a lower bound on the ground state energy because the ground state is suddenly compatible with all the constraints. And so if you minimize the energy, you'll necessarily be below the ground state. And so this gives you, if you can find a minimum, it's a lower bound on the energy. Okay, so to show you that this works, yeah.
Can I ask a question? So how do you know that you are not landing on some local minima? Or is there like some theorem saying that the bootstrap region you are after is convex?
Yeah, so I think not quite. And it is absolutely in its current formulation a weakness that we don't know how well it's done.
I see. So in practice, you are finding experimentally some local minima, and it just turns out that they correspond to global minima if you are lucky.
Yeah, let me see. So I think it is better than that actually, but yeah, let's say it's like that. I'm actually not sure about the convexity. It's just too bad that Shija is not here. I think he would know, but I'm not totally sure what the convexity. I don't think it's guaranteed convex, but I'm not sure.
I see. Yeah, thanks.
I mean, yes, that would definitely be something that would be good to know. All right, so so here are the results for one matrix. Yeah, right. So yeah, it's definitely true that this minimization is the weakest link in this approach. So right. So here's the ground state energy as a function of the coupling G. And this is the different values of L. Remember, L was the length of the strings that we were considering. And the exact answer, because we know how to solve this single matrix model, is that line. So basically by L equals 3, it's on, it just finds the answer already. And this is now the expectation value of x squared as a function of G. And again, by L equals 3, you're basically there. Okay. Here, this is a picture like what I drew before. So actually here you do see a certain, well, convexity, at least in this plane, right? So if you, now this is where you're actually minimizing, right? So this is a slice, right? You have this space of expectation values, right? And they have an energy. And so if this is a slice, the x squared slice of that space is a function of energy. And so you also can get excited states, right? So this this is the best guess for the ground state. But if you fix the energy to some excited level, then this would be the range at that excited energy of where the x squared can lie, right? And so it does start converging. And as a test, a certain state, by the way, I should also say this doesn't need eigenstates. It will work for any Gibbs state, any state that commutes to Hamiltonian, any density matrix that commutes to Hamiltonian. So in particular, the thermal state should be allowed. This is just the thermal state of the eigenvalues of the singlet sector. And so the thermal state is here. And so that it is allowed. Okay. But yeah, hopefully this plot helps a bit with the notion of the minimization, right? So you have this space, and you're minimizing the energy within this allowed space. Okay, so with some confidence, now hopefully.
Is there a way to access the density of states in this approach?
Yeah, good. Not that I know of, and yeah, that I absolutely had that thought as well, and I don't know how to do that. That would be, yeah, right. Yeah, I would, yes. I agree that's an interesting question to calculate the entropy, right, as a function of temperature, but I don't know how to do that.
Do you think it might be possible to, say, study expectation values in a given sector, like a joint sector or some other non-singlet sector?
I definitely think so. Yeah, yes, I don't, yes, you just have extra constraints on the, yes, I definitely think
because
that
could be very interesting. I mean,
yes, I agree. And you know, we were trying to run to two matrices, but and actually the adjoint sector is maybe not so far away from two matrices in a way. So yeah, I definitely think that I think is possible. Yeah.
Okay, great.
You just have a different class of operator, right? Because the Hamiltonian keeps you within the sector. I think. Anyway, I haven't thought about it, but I do think that should be possible. Yeah. All right. So two matrices. So now everything's in place really. So we took this model, no fermions at this point. So this is just seemed like the simplest. I guess maybe Hoppe was one of the first to study this model, right? So two bosons with a mass term and a commutative square. So the strategy is now going to be the same as for one matrix, except that it's worse because at length L, we have four possible operators, x, y, px, and py, right? And so the matrix that you get is not 2 to the 2L, but 4 to the 2L, okay? So a order 4 to the 2L. To help us a little bit, although not, I think, strictly necessary, we impose rotational invariance to reduce the number of independent variables. And so that means that so S, this generates rotations, the O2 rotations, and so we impose that. Okay. So I think this just means it's an eigenstate of angular momentum. Right. So now, indeed, related to these previous questions about convergence. So as far as I know, this two matrix theory is not solvable. And so it'd be nice to have a check on the results. And so we did something a little, I think it's a little bit nice. So I just wanted to mention it. We're going to use the Born-Oppenheimer wave function as a check, right? It is not correct, right? It's not that the wave function is in a Born-Oppenheimer limit, but so you can build the following. We're going to put one matrix, we're going to make one matrix diagonal, and then the other matrix is put in the instantaneous ground state of that, right? So you have right here, if x is diagonal, so I consider diagonal x's, and then this term gives me some potential a little bit like xi minus xj yij squared, right? And so the y's become harmonic oscillators, and you put them all in their ground states. Okay, that's just a wave function you can write. So that's this wave function. There's some wave function for the x's. Given this wave function, all the y's are in a harmonic oscillator state, and this has the form and their frequencies. There's the mass term, and then there's this term. Okay. A nice thing about Born-Oppenheimer that you may or may not remember from some undergrad class is actually you get both upper and lower bounds on the energy. So as a variational wave function, it of course gives you an upper bound on the energy, But actually, another thing, if you write down the effective Hamiltonian for the eigenvalues, and you just take the kinetic term, and then plus the the energies of the excited states, if you take this Hamiltonian, you can prove that gives you a lower bound that's always lower than the actual ground state energy. That's different from if you take the wave function and plug it into the full Hamiltonian. Okay, they differ by a term. So with this wave function, and the nice thing is now with this wave function is that we can evaluate it because it's a single eigenvalues, and we know how to calculate it with eigenvalues. Okay, so we get a rigorous upper and lower bound on the ground state energy using single matrix techniques. Right. So these are the results. I'm showing you now.
The omega ij depends on the x's, so there are absolute values of xi minus xj. It doesn't just separate into each eigenvalue behaving independently of each other.
Oh no, this is a couple. That's right, but you can still solve it, as you know very well. Yeah. So you can. That's right. This is not. These are not. Very good. This is not literally the matrix quantum mechanics that you would get from a single trace Hamiltonian, but it can be solved with the same techniques.
Okay.
Yeah, so you're right. The collective field, if you use collective fields, for example, the collective field action is non-local. It has an x minus y type interaction, right? So in the collective field energy, there's a term like rho x, rho y, square root m squared, g squared, x minus y squared. Yeah. So this is so rho is the eigenvalue density. You get some collective Hamiltonian, and this term here will turn into a term like this in the collective Hamiltonian. But you can perfectly well solve it using the usual methods.
Okay.
Thanks, as David knows very well. All right. So good. And so here, right? So this is a function of coupling, and so this is now three variables: the energy, the trace of x squared, and the commutator squared. And these are for L equals 3 and L equals 4. And remember, the matrix is getting bigger in this case. And these dashed lines are the upper and lower bound corresponding to these Born-Oppenheimer wave functions. So actually, this almost goes, I was a little bit surprised at how narrow this window is, and that almost contradicts what I was saying before about eigenvalues not being enough. I mean, here, just with eigenvalues, you can do pretty well. But okay. All right, so the best I can say is that L equals 4, this looks like it's somewhat close to convergence. And if we could get to L equals 5, which I think is definitely with a powerful computer doable, just not to what we had available at the time. My suspicion is to be very close to the L equals 4 line, but I don't know. Okay. Good, and this is the commutator. Anyway, so we can get, oh yes, very good, sorry, indeed. So actually this red line, I'm sorry, yes, this orange line may also be quite close to convergence because at infinite G, which is like the massless limit, oh sorry, we put m equals 1 here, okay. So large G is like small mass. In the massless limit, there are Monte Carlo results, simulations of this theory at non-zero temperature. And if you take in the the confined phase, at low temperature and you take it to 0 and you extrapolate this curve, you land exactly actually to 2 decimal places on the Monte Carlo results actually. So this orange curve is probably pretty good. Yeah. Good. Okay, so let me just wind up. So I've sort of whizzed through two approaches to matrix quantum mechanical wave functions. I think they're not perfect, but the importance of the problem behooves us to do what we can. And so one the Bootstrap uses positivity constraints, and the variational wave function approach uses neural networks. I showed you some new results for 2 and 3 matrix quantum mechanics. I think that more matrices, and the obvious question is something like, what can you say about maybe the BFSS ground state? Adding fermions to this story is in principle possible. It's just the number of operators that you have to worry about grows, right? So, already here we had 4 to the 2L. If you have some fermionic operators, life will get more complicated, but perhaps it's possible to use supersymmetry to constrain things even more. I don't know. But I definitely think it's not out of the question that one could do a supersymmetric theory with a lot of matrices and fermions. Non-zero temperature is possible. As she mentioned, it'd be great to know the density of states for that. But even if you don't, maybe there's some connection to black hole microstates. And also, I mean, the question, wave functions are not just expectation values, and to really bring out the quantumness of the problem, it'd be really nice to see if things like entanglement entropy can be accessed with these methods. Okay, that's all. Thanks.
Thank you, Sean.
So I had a quick question about the single matrix case. Say it's a bit of a, well, slightly out there question, but say you had never seen the Fermi C solution and you'd applied these techniques for the inverted X squared. Would there be any hint of that structure, that large N structure, from these techniques over here?
That's large. So firstly, coming back to actually a question earlier, we haven't looked at, I don't know what happens if you look at upside unbounded potentials. Probably
right. So one of the questions is how important is the boundedness? Because in that case, the unboundedness seems to be related to the emergence of something.
Literally, one of the constraints is the expectation value of 1 is 1, right? So we are using the normalizable wave functions, but I don't know what would happen if you lifted that. Relatedly, there are cases where you have moduli space of supersymmetric theories where there are moduli spaces. It might be possible to include those as well, but I don't know. Was that the main bit of your question, or was
or the Vandermonde, the structure of a Vandermonde, any of the structures that appear when thinking about these models from an analytic perspective?
Absolutely, and I think the answer is I don't know, but I think it connects to this question a little bit. The expectation values are not the most discerning observables that you ever encountered. I mean, commutator squares is a bit nice. So for example, something that you can check, I mean, this was known because it's known that this model has a normalizable ground state even in a massless limit, because the bosons lift all the classically zero directions. But okay, maybe say you didn't know that. Okay, maybe you didn't know that. Then what you can check here is that, like, trace x squared y squared over something like this. This goes to some order 1 number. It doesn't go to 0, right? It's not that the matrices don't start becoming commuting or something like that. So those, did I get a smile out of David Bernstein? I don't know, maybe. so this is the kind of more physicsy question, right? That you could address with these methods. For the case of a single, very good. Okay, so good. You have firstly I guess the logic is you want to find an observable that probes the question you want to ask, right?
Well, I want to connect the second part of your talk to the motivation of your talk.
Yes, I think.
Maybe I can help answer that question, if I can.
Yes, yeah, of course.
The positivity constraint is really closely related to the fermion picture, because you see, the positivity constraint forces the eigenvalues to be in a certain range and 0 otherwise. And that is essentially the Wigner distribution, which you know from fermions. So in some sense, that's why it's so important to impose the positivity constraint. That was the key. And when we did this kind of minimization some long time ago, we first ignored the constraints, and that didn't give us anything similar to fermions, really. And the positivity constraint assures that you are really close to that picture that you like to see, the fermions. because once the eigenvalues are forced into a certain range, then, you know, whether it's a semicircle or some other curve, no, that's not much different. So you are capturing that even with a few loops will capture that picture. Ah, sorry.
Let me add that's a good, maybe, I don't know if Henry was going to say this later. This is a point in Henry's paper that's clearest in the non-quantum case, but and totally, so following on from what you just said. So let's say here's the eigenvalue distribution, right? And it's 0 outside some range. And so if you take a function that is basically almost 0 here and non-zero out, then that will give you 0, right? So the trace of, let's call this some polynomial, this line here, or some polynomial. So the trace of this polynomial is close to 0, and so the fact that this thing converges is sort of saying that these positivity constraints are finding these polynomials that are supported outside of the Fermi.
Yeah, just
I don't know if that. Yeah, I think Dio's question was more would we rediscover the fermions if we didn't know about them? I mean, maybe.
One sort of minor point, which is if you can ask what happens in 0D matrix models if you consider upside down potentials past the critical point, right? And even analytically, you can just follow the solutions and you see that the solutions no longer satisfy positivity, right? So if you consider, you know, the simplest matrix model, which is trace x squared minus trace x cubed, right? Where the coefficient, you make the coefficient a little bit too large. You can still solve that in the saddle point approximation, but the eigenvalue density will no longer be real. It generally will be complex. So imposing positivity, I mean, you also see this in the bootstrap approach, where if you try to pass the critical point, you just find no possible solutions. So the bootstrap tells you sort of when your theory makes sense and when it doesn't. At least that's the hope. I'm not sure what happens in the quantum mechanical case, but I think the question about C=1 matrix model and inverted potentials is morally quite similar to the 0D case.
May I ask you both about something? I mean, Henry and Sean, it's a question which I'm chasing you with, Sean, over the wall during your seminars. Can you prove that that the positivity, in the best of the cases, when you impose all conditions, really leads not to an island, but to a distinct solution? Can one prove the theorem if positivity is imposed?
I prove this rigorously in the 0D case. It's essentially the statement that Sean just said, I think, which is that if you look at the space of all possible correlators, there's some cone in that space, which is the region which is allowed by positivity. And in order to prove the convergence, you would like to prove that the analytic solution lies on the boundary of that cone. In the one matrix case, you can, I think, rigorously prove that that's the case. It boils down to the statement that the eigenvalue distribution has finite support, so that if you consider polynomials of the form that Sean described, they have exactly 0 eigenvalue. So that proves that the analytic solution is on the boundary of that cone. And therefore, if you impose all possible constraints, you should exactly converge to it. I mean, the intuition is that if you slightly perturb, if you're on the boundary of the cone and you're just slightly off the solution, right, then since there's so many directions, you will most likely exit the cone. So that's not 100% rigorous, but I think that's a very strong argument.
It's an argument of a physicist, but the model is so simple and everything is known there, all the moments, you can express really everything through everything. It would be good to prove such a theorem.
Yes, I agree. The only thing I could say is, even in the cases where we can't solve the models, you can just check and see that there's some, well, yeah, certainly nothing rigorous that I know of has been said. So, but I suspect that similar statements could be made, because you could still consider the eigenvalue distribution of one of the matrices, say, And as long as it's compact, or even if it's not exactly compact, but has some exponential tails, I think you can still prove analogous theorems. But certainly it hasn't been done, and it would be nice to know rigorously.
It goes about the planar limit, so there should be no exponential effects. It's very direct. All the results are explicit for all momenta. Okay.
So I have a question. It seems that the complexity of this approach grows exponentially with the number of matrices. In BFSS, there are 9 bosonic and 16 fermionic matrices. That seems like a lot.
So I mean, I've only this thinking in this direction has not gone very far. But I think rotational invariance could be quite powerful. For example, so if you could restrict to operators, let's put the fermions aside for 1 minute. Okay, yeah. So, but say you've got 20 bosons or whatever, some large number of bosons. I mean, if you could probably restrict to operators, right? So if you start having traces, they all have to be contracted, right? And so actually, if you think of this kind of thing, this kind of structure doesn't care what range A is running over. Okay, so using rotational invariance, it may be possible to construct some subset of operators that are nicer. Now, as for the fermions, well, I think one just has to hope for supersymmetry to, because you see, yeah, indeed, even 3 matrices looks very difficult, right? And 4 looks very, numerically. So even with this simplification for the rotation invariance, the fermions then do seem to make it difficult. But maybe there's some, I don't know, I want to use a fancy like ring of operators, some closed structure of some kind of BPS operators, or some kind of closed structure, some set of operators that close among themselves under some operations, possibly involving supersymmetry. Then maybe, I don't know, you could hope that. So I think there needs to be more structure in terms of rotation variance, and supersymmetry had better help.
Don't the fermions also transform under rotations?
Yes, but no, exactly. So I think that doesn't quite buy you enough, because then you're still going to have like 4 or 5 matrices. Like it's as though it was a 4 or 5 matrix problem, and that's already looks tricky numerically. But maybe there are numerical improvements as well. I'm not the expert at that.
I will talk a little bit about this in the discussion, but one can review the Polchinski-Virial argument for bounding trace x squared in the BFSS model. One can view that as a sort of mini version of the bootstrap. So it shows, at least in principle, that you can obtain some analytical constraint on the BFSS ground state. Now, whether that can be improved by a lot, yeah, I'm not sure.